What's up, guys? Welcome back to my third video. Thanks for tuning in. Looking forward to get going on this one. So this video is going to be covering the scheduler for BareDrones 32. And the scheduler is essentially what allows us to run functions at specific rates. So as I kind of mentioned in the intro video, we might have different functions that we want to run at a kilohertz rate, so once every or 1,000 times a second. Then you might have some other functions which are a little bit less important, which you only want to run maybe like 5 times a second, such as like something that monitors the battery. You don't need to monitor the battery 1,000 times a second because it's not really changing that fast. Maybe you monitor it 5 to 10 times a second, and that kind of gives you the speed that you require without bogging down the CPU. So what we're going to first talk about is the SysTick interrupt, and how that kind of functions and how you initialize that, get that going a little bit, diving into how it works as well. And then we're going to talk about the scheduler itself, and that's going to go a little bit into linked lists, which is kind of a data structure within C and other programs, which is kind of how I implement calling functions and whatnot. So we're going to start with SysTicks, and if you're already kind of familiar with SysTicks, then you can skip past this part, but we're going to kind of dive into a little bit of how it works, and then how it's implemented in this case. So luckily for us, there's already a function provided to us that allows us to configure the SysTick interrupt with one fell swoop. And I know I said that this was going to be using no libraries, but I don't really count the SymSys libraries as part of using a HAL or anything like that, because SymSys is pretty common to all ARM microcontrollers. So we're going to go ahead and use that as well. But I'm still going to jump into the SymSys function and how that works as well. So we're going to take SysTick config and then system core clock, which in this case is going to be 260 megahertz. And then when I do my RCC video, I'll show you how you can get your clock up to 260 megahertz using bare metal programming, even though the clock configurator can do it for you, but that's no fun. So we're going to go here, SysTick config, and then system core clock divided by 1,000. We'll talk about why that's important and how that works. So if we jump into this function, you'll see all these different things. And if you look at the reference manual for STM32, if you look through here, you'll find like some generic references to SysTick, but nothing that really shows the value of the registers and whatnot, and it's not really all that helpful. So if we want to take the SysTick interrupt, we're actually going to have to go to the M7 reference manual, which is a generic ARM M7 reference manual for all ARM microcontrollers. So this isn't specific to ST, but it could be Texas Instrument, NXP, Atmel, anything that uses an ARM core will have this SysTick. And the SysTick is essentially a counter that will increment at a specific, at the clock frequency, and then it'll reset when it reaches a certain number. So it's almost like your generic timers, but this is common to all microcontrollers, and it's a pretty generic thing. So when you enable it, the counter will increment once every clock pulse up until a specific number, and they'll reset back to 0. And then if you enable the SysTick interrupt, every time the counter reaches a number, it will generate an interrupt before it goes back to 0. So we'll see a little bit how these are all set in this function, and then how we're going to implement the SysTick interrupt. So first thing we got to do is we have to load the value of that we want to basically overflow back to, or that when the tick reaches, it overflows. So we load it with ticks. So in this case, we do 216, 216 million divided by 1,000, which is going to be equal to 216,000, just like that. And I'll put a comma in there just so you can kind of easier see the decimals, or not the decimals, just the numbers. So we're setting this ticks to 216,000. And what this does is every time the ticker increments, and it's going to increment at 216 megahertz, and we want to reach a certain number so that it overflows back to 0. And if we want it to overflow once every millisecond, or at a 1 kilohertz rate, then if we set the overflow value to 216,000, then that will get us there. So the best way that I can think to explain this is probably graphically right here. So essentially, the counter on the SysTick moves up at 216 megahertz up until it reaches, for 1 second, up until it reaches, and then if you set the reload counter to 216 million, then it'll go to say 216
million all the way at the top. And essentially, each step takes 1 over 216 million, which is, pull the calculator out, 4 about 23 nanoseconds, I believe. Let me check my math on that. So 1 divided by 216, 4.63, sorry, nanoseconds, just about. So every 4.63 nanoseconds, this counter is going to increment. But what we want is we want to set an interrupt every millisecond, or 1 millisecond, which would be 1 kilohertz. That's what we want. So we want to get from 1 millisecond, but everything increments at 4.63 nanoseconds, then essentially what we can do is we can divide 1 millisecond by 4.63 nanoseconds, and what we're going to get is 216,000. And what this means is that when we get up to 216,000, that will be 1 millisecond has elapsed, or 1 kilohertz. At that point, we want to fire the interrupt. And in order to get to 216,000, we have to divide our rate by 1,000. So that instead of going up to 216 million, we're going up to just 216,000, at which point we reflow. And after 216,000 counts, we've reached 1 millisecond, we can reflow back to 0 and start over again. Say you want to do something like 8 kilohertz, which I think is what Betaflight runs at, then you can do 216 divided by 8,000, and then I'm not going to do the math for you on that one. But essentially, that's what we're going to put into our SysTick init function that SimSys provides for us. So pretty simple explanation for what's going on here. Just kind of want to lay it out graphically so it's a little bit easier to see.
So that goes into the load value, and you can see that appears right, the reload value right here. So it's called a little bit different in the reference manual, but that's essentially what it is here. And then we have to set the priority of the tick. So the SysTick interrupt is pretty high priority. It's going to be higher than all your peripheral interrupts, but lower than some things like the hard fault or the bus handler interrupts. And then you set the value of the counter to 0 to start off at 0, and then you enable it. So you enable the clock source as the internal clock, the tick interrupt, and then the actual enable of the internal peripheral. And that'll get you going for that. So you have your SysTick interrupt ready to go. And what this is going to do is it's going to call this function called the SysTick handler is going to be called at a 1 kilohertz rate. And you have to call this function SysTick handler. Unless you define it as something else somewhere else, SysTick handler has to be named as such. And what's going to happen is once every kilohertz, this function will be called. And now how do we use this to basically do the timing of our program? So every time SysTick handler is called, we have this global variable called frame counter, and SysTick uptime and these things I'm going to go into in a different video. These essentially help work with the delay functions like delay milliseconds, delay microseconds. So those are going to kind of go into that, and I'll talk about in a different video. But what's important here is this frame counter variable, frame counter plus plus. And essentially what's going to happen is once every kilohertz or once every millisecond, this function is going to be called, and frame counter is going to increment by 1. And it's going to increment by 1 until it reaches this variable frame count, which I have set to 1,000, at which point it will overflow back to 0. And now how exactly does this work in achieving what we want to do? So frame counter starts at 0, and the first time it goes through, it increments to 1. So if we start these all at 1, so I was just messing around with this earlier. So frame counter starts at 1, and we do this modulo operator. And you'll see why count 1000 is set to 1 right here in just a second. So you see frame counter modulo 1, or 1 modulo 1 is 0. And then we knot that and turn into a true, so 0 is false, 1 true, then this condition is set. And I'll show you in a second why the loop mask is important and how that affects the further operation of this. So every kilohertz, frame counter modulo 1 will always be 0. So every kilohertz, this condition will be set, which allows us to say, yes, we are, the 1 kilohertz condition is set, or 1000 hertz. Now, if we go down to the next one, it's going to say, okay, if frame counter, which is still 1, modulo count 500 hertz, which is 2. So 1 modulo 2 is 1, and not of 1 is 0. So if 0, that is false. so this condition is not set. And if you go through the rest of them, you'll see that none of these conditions are going to be set. So at 1, the only condition that's going to be set is the 1000 hertz loop. Now it runs through and the interrupt is fired again, and now frame counter increments to 2. So now 2 modulo 1 is still 0, and this condition is set again. And now when frame counter increments to 2, 2 modulo 2 is now 0, meaning that this condition is also set. So if you think through it, every time the frame counter is incremented to an even number, which is half the time, this condition will be set. And that's what we want, because half the time the 500 hertz loop condition will be set. So every single time, 1000 hertz, half the time, 500 hertz. And then if we keep on going through, you can kind of think logically through everything. We'll skip down to the 100 hertz, and the 100 hertz is set to 10, so that if frame counter is 1 or 2, then this will not be set. But say frame counter increments to 10, 10 modulo 10 is now 0, meaning this is true, and the condition for the 100 hertz loop is now set. And that means that we know that 10% of the time, the 100 hertz loop will be ready to go. And that goes all the way down to 1 hertz, which is going to be 1000. So the 1 hertz loop is only set when the frame counter is incremented to 1000, which would be only once a second, at which point we call this one. And when it's 1000, every single condition is going to be set. So all of these are going to be good to go. And that's when we know to run all the loops. And then so I set this variable loops checked, and that's just kind of like a checker to see if it's run through everything. We'll see where that gets implemented, at which point it runs back to the top, overflows back to 0, and then starts over again. So that's what's important inside the SysTick handler function. So moving on from there, how do we actually use this? So you can see that we have this variable called loop mask, and the implementation of this is a little interesting, and I'm going to try to explain it the best that I can to kind of show you how this works. So one of the first things that we're going to have to do is kind of give a small talk on to linked lists and that data structure in C and other programming languages. And I'm not going to go super into it because I'm fairly new to the topic, but essentially a linked list is a data structure in which each element of the structure points to the next element. So as you can see in this diagram right here, you have A, which contains the data for A, but then also it contains a pointer to the next element, which is B. B contains a pointer to C. C contains a pointer to D. And then D, which is the last element in this list, points to the null pointer. And it basically says, like, hey, the list has been terminated. And linked lists have a distinct advantage over arrays in that arrays can be called sequentially, but arrays also have to use the same type of data structure, because when you initialize an array, it has to use the same structure. And also, it's very, very difficult to clear arrays or to insert an element in the middle of an array. So like say you had element Z that you want to put between B and C. In an array, you basically have to shift individually each element, which is a pretty difficult thing, where if you want to do a linked list, if say you have element Z that you want to put between B and C, you could say, okay, B no longer points to C, but B now points to Z, and then Z is going to point to C. And that's as easy as it is. And I'm not going to go too much into these functions. If you want to read about it more, I would highly recommend checking out Geeks for Geeks and looking at their tutorial on it, because they do a much, much better job explaining it than I ever can. And I think that reading things like these is definitely better. If you want me to go into it more and kind of talk through this forum on Geeks for Geeks, then I can absolutely do that. But I would recommend reading this to get onto it. So there's a few functions that we use, which I'm not going to lie, I took straight from the website. No such thing as coding without Google. So there's one function which pushes. So essentially this pushes an element to the front of the list. So you can see given a reference to the head, inserts a new node in front of the list. Then we have insert after. So given like a node in the list, you can insert another node after that node. And then append essentially puts a new function at the end of the list, or a new element at the end of the list, given the reference to the head. So right now we only use the append function, but there's also going to be some uses for the insert after and the push function if you need to do so. So what we essentially do here is we create an array of linked lists, and each element in this array is contains all of the functions for a particular loop. So to kind of type it out a little bit, exec tasks of 0, so the first element is going to contains all the functions for the 1 kilohertz loop. And then all exec tasks of 1 contains all the functions for the 500 hertz loop. And each function points to, so each element points to the next function to be executed. So in the case of the first one where we have just read MPU 6000 data, there's only one element here, and the 1000 hertz array element, and it points to the null pointer because there's nothing after it. For the 500 hertz loop, we have a lot of different functions. So the first element is compute rotations 500 hertz, then it's update IMU, then update attitude, and essentially each function says, okay, here I am, here's my function. The next thing to do is go to the update IMU function. The next thing to do is update the attitude, all the way down to the mix table, which says, okay, I'm the last one, the next one is null. So at that point, it knows that it's done. And then it keeps on going all the way down. So we have 500 hertz, and then we have a 200 hertz, 100 hertz, 50 hertz, 10 hertz, 5 hertz, 1 hertz. Not every single loop is used, but essentially we have 8 different loops, and each loop contains a linked list of functions that are to be executed. And then when we say run, exec task contains all of these functions in their arrays. So if we run exec tasks, then first the thing that it does is it checks if all the loops have been checked. So as you can see here at the bottom, we have loops checked equals true when all the loops have been checked. So it goes there, and if it's been checked, so it basically holds there until it's been checked, and then once it is, loops checked is false. And so now loop to run essentially tells you, hey, which element in our array of tasks do we want to run? So it starts off with the 1000 hertz loop, which is just 0. So for a loop to run, less than total loops is 8 because we have 8 different loops plus plus. And then so now here's the mask thing that I was talking about. So the 1000 hertz loop has a mask of 1 push 0 times. So this looks like 0x or 0b, 000, 000, 1. I'll put a space in there, and I missed a 0. So that's what the mask for 1000 hertz loop. So loop mask starts off at 0, and then we OR it with mask 1000 hertz, and now it becomes 000, 1. And then what this does is it goes to here and it says, okay, if loop mask shifted to the right, loop to run times, has a 1 in that spot, then it means that that function is ready to be run. So loop mask, in this case, loop mask is going to be, I'll comment down here, 0b, 000, 1. So that's what loop mask is going to be. And if we shift it to the right 0 times, which is what this is starting at, and we end it with 1, then we know 1 ended with 1 is 1. That's true. So now we're going to go through and run the 1000 hertz loop. Now, say for the 500 hertz, so say the 500 hertz condition is set, then we're going to do loop mask is mask 1 shifted over 1 time. So this is going to be 1, 0, 0, 1, 0. And now, next time we go through, we're checking, we're incrementing loop to run to 1. So now loop mask push to the right 1 time is just going to be 0x, or sorry, 0b, 000, 1. And 1 ended with 1 is true, so we know the 500 hertz loop is ready to go. And this goes all the way down the line. So the 200 hertz loop is 1 shifted over twice, 1 shifted over 3 times, 1 shifted over 4 times, and each time it pushes the mask to the right however many times to check if that loop is run. And then if the one bit is set in that place, then it knows, okay, this loop is ready to go. And then what it does is, first I like to have some checking. So basically it takes the current system time in microseconds, and then it checks delta time, which is essentially the time between loop calls. So I'm just kind of trying to, this is almost like a check to make sure that it's actually taking the right time between loops. and then this is a little bit of like setting old variables to the new one, and then now this is what runs all the tasks in the loop. So essentially what I do is I pass in a reference to the head of that list and the loop to run. So if loop to run is 0, meaning the 1 kilohertz loop, then we're passing head ref of 0, and that goes to run all tasks. And then while task is not null, because remember the last element of the array points to the null pointer. So what it does is it does task run the function, and then task next, and then it goes to the next function, and it goes through, and if the next function isn't a null, then it'll run that function. Goes through, if it isn't a null, it runs the next function, and then if the next pointer is a null, then it drops out and says, okay, we're done running all those tasks, time to drop out. And then it unmasks that variable, that bit. So over here we had to mask the bit, and now we have to unmask it right here. So we shift it over however many times, and then do an and, opposite and then now we do the execution time of loop to run micros minus the current time. So this basically tells us how long this loop actually took to run. And this is important just because we need to make sure that everything kind of stays within this time frame, that if we're reading MPU 6000 data at a 1 kilohertz rate, if that function actually takes more than, I say, like a few microseconds to run, then it's going to start interfering with other stuff, and that's pretty bad. So we got to make sure that things are staying in line. This is kind of a good check to make sure that things are doing that. So this is essentially how the scheduler works. It's a little convoluted in nature, and there's a lot of weird C kind of things going on here. But definitely take a time to walk through the code, and linked lists, definitely recommend checking out this video right here to try to, this article right here to really get a deep dive into it. And they're pretty cool and they're very interesting, and definitely have a pretty cool application here. So sorry, I think that video got a little bit longer than I was hoping to go for, but hope you guys learned something here. Next video is probably going to be on delay functions and how we can initialize those and then use them in our drone program. Thank you for sticking around, and I'll see you next time.